Hello everyone, welcome to the class. Today we will start with where we stopped in the last class. Now we were studying plane wave propagation in anisotropic media, and in the last class we derived determinant from the coefficient matrix, and we said that coefficient matrix must be equated to 0, and from that equation we should get two values of NW square. Now we will consider a case of uniaxial crystal here, wherein the refractive index along x and y axis are equal, and we assume that they are equal to n naught, which represents the O wave refractive index, and along z axis and z, which is the refractive index along z axis, is equal to n e. Now nz represents the refractive index along z axis, and we assume that it is equal to n e, the E wave refractive index. Now for a uniaxial crystal, x and y direction can be arbitrarily chosen as long as they are perpendicular to the optic axis. Yeah, because we know that in uniaxial crystal epsilon x is equal to epsilon y, and which is not equal to epsilon z. It means epsilon z, that is the permittivity along z axis. Now the z axis is an axis which is unique. Yeah, therefore the x axis and y axis, they would be identical, and this is why the x and y direction can be arbitrarily chosen, and they must be perpendicular to the optic axis, and we choose optic axis along z axis. The y axis is chosen normal to the plane defined by k, that is direction of propagation, and the z axis, and z axis will lie in the same plane, of course, yeah, and which is given by this figure here. This is the direction of z axis, this is the direction of k axis, and y axis is perpendicular to the plane. Which plane? A plane which is made by z axis or optic axis, and the direction of propagation, which is k. Now since k is direction of wave, and say it is at an angle psi with respect to optic axis or z axis, then kappa x would be sin psi, kappa y is equal to 0, of course, because y is perpendicular to wave vector k direction, and kappa z is equal to cos psi. Just to remind you, what are these kappa x, kappa y and kappa z? They are the components of unit vector kappa cap. Okay, kappa x, kappa y, kappa z are component of unit vector kappa cap. Unit vector kappa cap is along wave vector k direction. Okay. Now from the three component equation which we derived in our last class, now they take these form. Okay. The new modified form of these equations are given by equation number 69, 70 and 71 respectively. Okay. Now you see here in first equation, this equation number 69, which has E x and E z term, and equation number 71 also has this E x and E z term. Okay. And both these equation, they do not have any E y term. E y dependence is absent in equation number 69 and 71, while in equation number 70 we do have E y, but this equation does not have E x and E z. Okay. Now since two equations involve only E x and E z, and one equation involves only E y, we have following two independent solutions. And what are those two independent solutions? The first solution is solution wherein we assume that the y component of the field is non-zero, while the x and z component of the field is 0. Okay. With this, E y is not equal to 0, and E x and E z both are 0. Okay. Now since both E x and E z is equal to 0, then we cannot use 69 and 71. What is left with is equation number 70. Okay. Since E y is not equal to 0, then this term must be equal to 0. Yeah, because E y is not equal to 0, and on right hand side we have 0. Therefore in equation 1, this coefficient must be equal to 0, and from here we can write N w is equal to N w naught, which is equal to N o. Okay, this quickly comes from equation number 70. Yeah, n w is equal to n naught, and we assume that it is n w naught. Okay. Now, once the value of refractive index is known, we can easily calculate the wave velocity of such a wave. The wave velocity would be given by c by n naught. Okay, and we represent it as v w naught. But do remember, all these things are valid only for E y is not equal to 0 and E x and E z is equal to 0. It means electric field is pointing only along y direction. It means the wave is y polarized. Then if the wave is y polarized, then we have ordinary refractive index. Okay, a y polarized wave in such a situation is called O wave. Okay, do see here in this figure, y polarized wave, since it is y polarized wave, the direction of E is perpendicular to k as well as optic axis. Okay. Now, since the wave velocity is independent of the direction of the wave, it is referred to as ordinary wave. You see, there is no dependence of psi. Okay. The velocity is independent of the direction of propagation. Our refractive index is independent of the direction. It is a constant quantity, irrespective of the direction, it is the same. Okay. Now, further, for the O wave, D vector and E vector is y polarized. Okay, because the D is in the direction of E. Okay. Why D is in the direction of E? Let me remind you that these were equation 69, 70 and 71. These were the three equations which were written in the component form, and these are nothing but D is equal to epsilon E relation. But since we are dealing with anisotropic crystal, epsilon is the tensor, and therefore we wrote D is equal to epsilon E in component form, and this gave us these three equations. But now we are solving for a case wherein E y is not equal to 0 and E x and E z is equal to 0. Okay. Now, with this we got the refractive index is a constant quantity, therefore, velocity is also a constant which is direction independent. Therefore, the scalar relation between D and E now becomes valid. Okay, D would be equal to epsilon E, and epsilon is a scalar quantity, and therefore, D points along E. Okay. And therefore, for O wave, D vector and E vector both, because they are pointing in the same direction, are perpendicular to plane containing k and optic axis. The wave vector k and optic axis forms a plane, and D and E they both are perpendicular to this plane, and which is shown here in this figure. See, z is the direction of optic axis, k is wave vector propagation direction, the orientation psi is equal to theta here, and both D and E are along y. Okay, and they are perpendicular to the plane of this paper, and this plane of paper is made by optic axis and the ordinary wave propagation vector. Okay. If the wave is O wave, then we draw this figure. Okay. You see that H is along y, yeah, it is coming out of the paper. Now, this was all about first solution where E y is not equal to 0 while other two components were 0. Now, let us go pick the second solution which says that E y is equal to 0 while E x and E z is not equal to 0. So, let us go back to the three component equations. Now, in this equation, now since E y is equal to 0, then this term will not be equal to 0 while E x and E z is not equal to 0. Therefore, this time we will just look into these two equations, the 69 and 71 equation, and from this equation 69 and 71, let us write the ratio between E z and E x. From 69 we get this value of the ratio, and from 71 we get this expression for E z upon E x. After little bit of mathematics, we get the expression for n w square, and this is the expression which we saw in our first few classes of introduction to double refraction. Okay. There I showed you the velocity of E wave is given by this expression. Okay. Then once the refractive index is known, we can easily write the expression for the velocity using this relation, and you now see that the both the velocity and the refractive index are direction dependent, they depend upon the angle of wave vector with the optic axis. Okay. Now, since the wave velocity is dependent on the direction of the wave, it is referred to as extraordinary wave or E wave. Okay. Now, for extraordinary wave, since E y is equal to 0, d y which is equal to epsilon y into E y, this would be equal to 0. The displacement vector d associated with extraordinary wave lies in the plane containing propagation vector k and the optic axis, and is normal to k therefore. Yeah, since y component of the displacement vector is 0, it means displacement vector must be in xz plane, okay, which is the plane of the paper and is shown here. This is the direction of optic axis, and if say k is oriented at angle psi with the optic axis, then d which is perpendicular to k would be in this direction, and this angle would be 90 degree. D would be perpendicular to k. This is what we also seen while solving the equation in the last class, in the last lecture. Similarly, say this is the direction of pointing vector, okay, then E field, electric field would be in this direction, and this angle would be 90 degree now. Okay. Pointing vector will make an angle of 90 degree with the E field direction, and wave vector k will make an angle of 90 degree with the displacement vector direction. Okay. Now, whether psi would be larger than phi, or phi would be larger than psi, or psi would be equal to phi, all this depend upon the material properties. Okay. Example, we will treat one case. Now, in order to determine the angle phi, okay, phi is this angle between S and K is phi. Okay. Psi is the angle of orientation of K with respect to optic axis, and psi plus phi is equal to theta. Okay, these are given. Now, we want to know the relative orientation between S and K, which is phi. Okay. How to get phi? Let us see what is dz by dx. From the figure, the z component of d would be in this direction, and x component would be in this direction. Therefore, dz upon dx, dz is in negative z direction. Therefore, dz upon dx would be minus of tan psi, yeah, because d is perpendicular to k. Okay. Therefore, tan psi would be dz by dx, and we know that d is equal to epsilon e. Therefore, dz would be epsilon z E z, and dx would be epsilon x E x. And similarly, from figure, E z upon E x, which is E is pointing in this direction. Therefore, E z upon E x, since E is perpendicular to S, we will now therefore take this angle theta into account. Okay. Therefore, E z upon E x would be minus of tan theta, and theta is equal to 5 plus psi. Therefore, E z upon E x would be minus tan 5 plus psi. Okay. Now, let us substitute the expression of E z upon E x into equation number 77. Okay. The expression of E z upon E x from 78 is now substituted in equation number 77, and this gives this relation, okay, where any square comes in the expression of epsilon z, and n naught square comes in the expression of epsilon x. Now, from here, from equation number 79, if you just simplify it, you will get the expression of phi. So, now for negative crystal, we know that NO is larger than Ne. Okay. And if NO is larger than Ne, then this term would be larger than psi, and this quantity on the right hand side of equation number 80 therefore will be positive, and it says that the ray direction is away from the optic axis. If phi is positive, it means S would be away from the optic axis. It would look, the position of S would be in this direction from K, okay, because phi is positive. And what is phi? Phi is orientation of pointing vector s with respect to k direction, and positive phi means phi is in this direction. Okay, and this happens in a crystal for which NO is larger than Na, that is for negative crystal we will have k in this direction and s in this direction. This is positive phi. For positive crystal, NO would be less than Na, and phi, therefore, since NO is less than Na, this quantity would be smaller than psi, and therefore, phi would be negative, and it means that ray direction means direction of pointing vector, it will be towards the optic axis. It means in this particular case, if k is pointing in this direction, then s would be pointing here. This would be the phi which is negative. Yeah. With this I end my lecture, and this also finishes the second last module, that is module number 11. From next lecture onward we will start module number 12, which is totally dedicated on the applications of whatever we have studied till now. Okay. Thank you for joining me. See you in the next class.